All right, so we continue line coding as module 3. There's two parts to this module. The first is just theory, which is, I would say, just drawing a bunch of waves. The second is a bunch of derivations. Now, derivations are annoying, but I think there's a way to maximize marks without wasting a lot of time trying to study it. But we'll go through the derivations anyway. The first is the theory part. So there's three types of waveforms you should remember. The first is unipolar, which means the bit is high, then the amplitude is plus Q. When the bit is low, then the amplitude is zero. Polar, since it's not uni, it's like polar, plus Q minus Q instead for high bits and low bits. For bipolar, it's plus A comma minus A for consecutive or consecutive ones and zero for the bit zero. So now something to note for bipolar that it's also known as pseudo-ternary, and plus A and minus A are assigned alternatively to bit one. So they don't need to be 1 1 in a row. There can be 1 0 1, but the first one will have an amplitude of plus A and the second one will have an amplitude of minus A. So the bits of one aren't necessarily consecutive. So now for the pulses. So the first is NRZ, which is non-return to zero. So during the time period TB, it won't come back to zero until the end. This goes on normally. The second is return to zero. So this is where it returns to zero at half the time period. So if your frequency is FB, your time period is TB, then your wave form is going to come back to the T equals zero, or like amplitude equals 0 point at TB by 2. And then there's a third type known as Manchester. So after TB by 2, it inverts. So RZ, it comes back to 0. Manchester goes from plus A to minus A for high bits. So if it were a lower bit, then it would go from minus A to plus A. So that's how Manchester works. So the techniques are just, well, assume that the data is 110010. Unipolar NRZ, you'll see that for high bits, your amplitude is plus A, and for low bits, your amplitude is 0. Fairly simple. For polar NR0, you'll see that your amplitude is plus A and minus A for high bits and low bits. For bipolar, you'll see that the first high bit, your amplitude is plus A. The second high bit, your amplitude is minus A. And then you have a bunch of zeros which don't really matter. They're zero. And then you have another high bit, which is an amplitude of plus A because minus A was the last one. And similarly, we have return to zero. This is unipolar RZ. So you see that in each time period, they come back to zero for the high bits. And then for low bits, they don't really do anything because unipolar is zero for 0 bit. And again, in the last but one high bit, it goes up and comes back down in half the time period. In polar R0, the same thing happens, but here, even for the lower bits, we have a minus A value. So they also come back to the top from the bottom at TB by 2. Bipolar R0 is again the same as unipolar, but here the alternating values of plus A and minus A exist. Polar Manchester is just the same as everything else, same principle. So polar is plus A and minus A. For Manchester, it comes back and it inverts. So you have an inversion in both of the high bits from top to bottom. And then for the low bits, you have an inversion from the bottom to the top, then vice versa. That's all for drawing. So the only question that'll come out of this is them giving you an input sequence and asking you to draw like all of these waveforms. Next is the derivation part. Power spectral density of line codes is what they'll ask you to derive. So there are three steps here for any derivation, um, even if it's non-return zero or return zero. The first step is to always find the Fourier transform of the input signal. So for non-return zero, the input signal is always going to be 1. So you draw the diagram there. And the Fourier transform formula is given by x of f is the integral of the time limits times the signal times e power minus j2 pi ft dt. Now, if you know a bit of trigonometry and integration, which you probably do after all these courses, then you should probably be able to derive this. I was not. I had to struggle, but you know, these trigonometric formulas are annoying to remember. Um, Also, it's just boring to look at, I guess. But x of f eventually simplifies to sine of pi f dv by pi f. But we have the definition of sinc theta, which is sine pi theta by pi theta. So we eventually get x of f is tb sinc ftb. This is probably annoying to remember, but it's more the additional motivation for you to remember this is that this same Fourier transform of the input signal first step is going to show up for every single return zero derivation ever. So any derivation, this is just probably free 2 to 3 marks for you to like get out of it. Just like take the input signal, calculate, pretend to calculate at least the Fourier transform, draw that small mini waveform, and write TB sync FTB. So the second step for all of these derivations is to find the autocorrelation function. Is so this is RA of n, and first you note the variation in amplitude, which is here since we're calculating unipolar, we already know that it's plus A and zeros for high bits and low bits respectively. So the next thing you just need to remember is that RA is always given by the mean of AL times AL minus n. So RA of n is the E of AL times AL minus n. There are always, in the second step, two steps we need to calculate for. First for n equals 0 and the second for n equals 1. So first for n equals 0, RA of n becomes E of AL square because A of L minus 1 is A of L. So RA of 0 is E of L square. Here's like where you draw this table and you put 0 and 1. And this is essentially like a truth table of sorts. So 0, 0, AA, what does your AL value become? 0, AL square. So the probability of your bits being that way is half half, obviously. So that's your table. And then eventually what you have to do is like sum AL square and the product of the products of AL square and B. So here it would be 0 times 1 by 2 plus A square 1 times 1 by 2. Like this looks annoying at first, but trust me, once you get through all these derivations, they'll get very simple and probably monotonous as well. So your area of 0 is A square divided by 2. The second case to calculate for is if n is not equal to 0. And here AL times AL minus 1 sticks as it is. And you have again a truth table of sorts. So 0, 0, 0, A0, AA, which is all the possible outcomes. So you have 0, 0, 0, A square as a product, and then the probabilities you have evenly divided. Again, so it becomes 1 by 4 times 0 plus 1 by 4 times 0 plus 1 by 4 times 0 plus 1 by 4 times A square, which is A square divided by 4. So your eventual RA value is A square by 2 at n equals 0 and A square by 4 at n is not equal to 0. This is the second step complete. And here's where you should probably expect like 5 marks already in the derivation, I think. The third step is the Einstein-Wiener-Kinch, whatever, EWK theorem. And the formula here is P of f is 1 by TB x of f the whole square and times the summation of RA of n e minus j2 pi f n TB. Now, it's a very annoying calculation in between, but essentially the first step you expand everything, you substitute everything in, and well, you take the n equals 0 term out of that summation, you make it independent. So you put a square by 2 elsewhere, and you mark an n not equal 0 under the summation sign. And then because the n is equal to 0 term is already taken out, you replace all of that, and then you have some annoying Poisson's formula. Honestly, nobody cares about all this. Just write the Einstein-Wiener-Kinstein equation. Hopefully, your professor's like understanding enough, and you eventually get like P of f is a square TV by 4 sinc square FTB plus a square by 4 delta of f. Of course, if you want to go through the derivation, it's fully written out, be my guest. So, yeah, that's your final formula for this. The second is polar energy. Again, the same 3 steps. Find the Fourier transform. We have it already. Find the ACF and then use UWK. So here again we repeat. So here you notice that AL is different because for polar it's plus A and minus A. You have minus A wherever 0 is. So minus A square, and then eventually you get RA of n equals 0 equals A square. Then for n is not equal 0, you get um 0. So your RA value is A square where n equals 0, 0 where n is equal to not is not equal to 0. So that is a difference. And then again you use EWK, and then this translates eventually to A square TB sine sinc square of FTB, and that's the graph that you get. Bipolar is where there's a small difference. You have the same steps, but here, since it's alternating values of A, you have to account for a few extra possibilities in your um, truth table to find autocorrelation functions. So you have plus A, minus A plus A, and then you have the corresponding values below. And obviously, since there's one probability divided into two, that 1/4 is then halved each. So for the 1 bit sequence, you have to like make sure that all plus A minus A combinations are found. So for bipolar alone, you are asked to, or not asked, you're supposed to find autocorrelation for n is 0, n is 1, and n is greater than 1. This is different compared to previously when we just had to do n equals 0 and n is equal to 1. N is not equal 0, sorry. So this is a difference, right? And then eventually you get the three values: a square by 2 for n equals 0, minus a square by 4 for n equals plus or minus 1, and 0 wherever n is like greater than 1. Again, you use Einstein-Wiener and you make the substitutions, and you eventually get P of f is a square TB sinc square FTB 2 sine square FTB. There's your waveform as well. Manchester has a doublet pulse and uses a slightly different Fourier transform of the original signal. And then you eventually get TB sinc FTB sine pi FTB by 2. Your autocorrelation function is the same as polar. So you get a square and 0 for n is 0 and n is not equal to 0. Use the same Wiener, whatever, Kinstein to get the power spectral density is a square TB sinc square FTB by 2 sin sine square pi FTB by 2. So that is for Manchester. Now RZ is actually pretty much the same, except you have to divide TB by 2 into TB by 4. So your values essentially get divided by 2 wherever you have TB. So TB by 2 sinc of FTB by 2 is your Fourier transform, but your autocorrelation function calculation remains the same. Your Einstein-Wiener remains the same, except you replace, like wherever you make your substitutions, you make them differently. And everywhere else it's the same. So the only difference for RZ that I observe is that your TB gets replaced by TB by 2 in the Fourier transform of the input signal. Eventually, you get slightly different values for power spectral densities. For polar, you get a square TB by 4, sinc square of FTB by 2. For bipolar, you get a square TB by 4, sinc square of FTB by 2, sinc square of pi FTB. Yeah, that's all for that module. So the next is the inter-symbol interference module. This is a block diagram here, pulse generator, there's a transmitting filter, there's a channel, there's a receiving filter, and the destination device. So as a baseband binary data transmission system, you basically get an input, which is x of t is sigma of the summation of ak, which is amplitude, times g of t minus ktb. And the output is y of t is mu times summation of k equals minus infinity to infinity akp of t minus ktb. This is just theory that you should know. There's no numerical coming out of this part of this module. So the channel is noiseless and dispersive in nature. It's a coaxial cable and it's an optical fiber. So then you have to take the Fourier transform of your input and your output. And you have to note that the h of f is the sum of the um, transfer functions of your three filters, the two filters and the channel. The product, sorry. So your H becomes the product of the three HR, HC, and HT. And where your mu is a scaling factor, your output is sampled at T is ITB. Your equation becomes mu times epsilon naught of k equals minus infinity to plus infinity AK times B of I minus k times TB. So eventually the formula that you get is y of ti is mu ai plus mu of summation of k is not equal to I ak p of I minus k tb. This is the formula that you have to remember. But the important part to note here is the contribution of the ith bit is mu ai. So that's the important part you have to remember. The second term is the effect of all the other bits before and after the ith bit. Intersymbol interference is this, the interference effect that is caused by the rest of the bits that we don't really care about. against the output that we really need. There are two ways to eliminate ISI, which is first the proper design of pulse spectrum and filters, blah, blah, blah. The second one is the individual spectrum with the filter should be separated by a period of TB. How do you detect data by controlled ISI? So let the sample of the received filter be y of ti. So let's say you get three terms, ai plus ai minus 1 plus n of t. So ai is the amplitude of the bit that we have. Ai minus 1 is the amplitude of the previous bits, and n of t is just noise. So we can ignore everything and we can just say that we take two consecutive bits, and this bit ai can take a value of plus 1 or minus 1 for a high bit and a low bit. So with these combinations, you do duobinary signaling. So what you basically do is you let the input, for example, let the input sequence be bk, and let each bit be 1 or 0. You have to do NRZ encoding for this. So if the bit in your sequence is the high bit, that is 1, then you replace that with AK value of 1. And then if it's 0, then you replace that with minus 1. And then you encode this value, which is you take the output of the encoder, which is CK is AK plus AK minus 1, and you reconstruct the original signal by a prediction of K equals CK minus A cap K minus 1. It's simpler if you see the table here. So let 00110100 be your input sequence. Let the NRZ encoding be minus 1, minus 1, 1, 1, minus 1, 1, minus 1, minus 1. Here you'll notice that wherever 0 was, we replaced it with minus 1. Ones all remain the same. Now we take this and we take the CK of this. So obviously the first one, since there's no AK minus 1, we leave it as such. The second one is minus 1, and then AK minus 1 was minus 1. So for the second column of the CK, we have minus 1, which is minus 2. The third column is 0 because 1 minus 1 is 0. So the one above it minus um the sum of that and the one before it is 1 plus of minus 1. So AK plus AK minus 1. So the whole row, you'll see that they're actually the sum of the bit above them and the bit next to the one above them. The last one, for example, is minus 2, which is the sum of minus 1 and minus 1. And then what you do is you reconstruct this by subtracting the prediction of AK minus 1 from CK. So you take a cap of k, then it becomes minus 1, 1, 1, minus 1, 1, minus 1, minus 1. And then eventually you have your output signal as the reconstructed signal. Then the final part of theory for that module is that one way to study ISI in PCM or transmitter systems is to apply the received wave to the vertical deflection plates of a oscilloscope and a sawtooth wave the horizontal deflection plate. Resultant waveform you get is as such in this diagram. You have three things to note in the diagram. The first, which is slope, which is the slanting of the wave. Second is the distortion of TS, which is the gap between the first and second line on top. The distortion of zero crossing is at the intersection point. The area marked 1 is the margin over noise, and the area marked 2 is the interval over which the wave is sampled. So these things are the ones you need to mark in the diagram because often the question from this module will be very direct. So there's a few lines of theory you have to note. The width of the eye opening defines the time interval over which it can be sampled. The rate of closure of the eye determines the sensitivity of the system to timing error. The height of the eye opening determines the margin over noise, and the eye completely closes when the effect of ISI is very severe. That's it for that module. Next, we have the information theory and coding module. So this is a study of a communication system, blah, 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 condition of occurrences, blah, 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 doesn't really matter. What really matters is entropy in that formula, h equals minus summation of pi log 2 pi. Pi is probability of every single thing in that entity. So the amount of information is then given by I is equal to log of 1 by pi. The important thing again is to remember the value of entropy here. So this is an example. So we get this source which is delivering S1 with a probability of P of 0.4. Probability of 0.6 is delivering S2. So here if we want to sum the probabilities and take the entropy, it's a 4 times log 2 of 0.4 plus 0.6 of log 0.6. And then the negative of all of that is the formula. So one useful thing to note if your calculator doesn't have logarithm to the second base is that log 2 of something is equal to log 10 of something divided by log 10 of 2. So eventually you get that value for your H or entropy. And then you have 6 outcomes. Again, you have each outcome is a probability, and you're asked to find the entropy and R. The rate of information is given as RH, where the small r is outcome rate. So again, you just substitute the values and um, you get the same answer as I've written. The next is mutual information, which is the measure of mutual dependence or the amount of information you can infer from one random variable for another. So again, most of these formulas are not useful. The one that you need to remember though is the one marked number 5. H of x is the summation, the negative summation of p of xi log of p of xi. The same for y. And h of x comma y is the summation of every single element for x and y. The second set of important formulas is the one next to it. H of x given y is h of xy minus h of y. So the one in the base is the one subtracted. H of y given x is h of xy minus h of x. One in the base is again subtracted. So an example of this very similar to Markov chains or like hidden Markov models in AIML. So you're given a path and you're given the probability of going from one place to another. So x1 to y1 is given as 0.25. So similarly, you have a bunch of paths and a bunch of variables, and you model this by saying, here I'll draw a matrix P of x comma y, x1, x2, x3, and y1, y2 are the outputs. You draw the probability of going from x1 to y1 in the column row of x1, y1. So similarly, you fill up the matrix. And here, to find the probability of x1, you sum the row of x1. So 0.25 plus 0.25 is the probability of x1, 0.15 plus 0.15 is the probability of x2, and 0.1 plus 0.1 is the probability of x3. Similarly, for y1 and y2, you sum the whole column and you get the values. And then you use the same formula for entropy, right? So since you have for y1, y2 of 0.5 and 0.8, sorry, 0.5 and 0.5, you do minus 0.5 log 2 0.5, again minus 0.5 log 2 0.5 sums to 1, and then h of xy is the entirety of the matrix, which comes to 2.484. Then you use the same value, substitute everything. 2.484 minus 1 is 1.484. H of y of x is 2.484 minus 1.484, which is 1. The last thing in this module is channel capacity theorem. So by principle, a way for communication systems to transmit information with an arbitrarily small probability of error and providing a good information rate of R equals R times max of I of x of y. This is known as Shannon's theorem as well. So the basic thing is your capacity C should be bandwidth times log 2 base uh, of 1 plus SNR. So as long as R is lesser than or equal to C, the transmission goes on without error, even if there is noise. And if R is greater than C, then your probability of error is going to approach unity. And there's a simple numerical that uses substitution for that.